The Golden Gate Bridge. The Golden Gate Bridge was designed to move, not resist nature. On hot days, the bridge can expand up to 3 meters, and during strong winds or earthquakes, it sways on purpose, absorbing energy instead of breaking. Its steel cables are made from 27,000 individual wires, tightly spun together. If just one wire fails, the rest carry the load, a built-in safety backup decades ahead of its time. The famous orange color isn't aesthetic alone. It was chosen for high visibility in fog, corrosion resistance, and to blend with the natural environment. Engineering disguised as design. Danyang-Kushan Bridge. At 164 kilometers long, This is officially the longest bridge in the world. Stretching across rivers, lakes, wetlands, and soft ground, the bridge carries high-speed trains through some of the most unstable terrain imaginable. The real challenge wasn't length, it was stability. Instead of fighting weak soil, engineers elevated the entire railway on thousands of pillars, spreading the load evenly and isolating the tracks from ground movement. Built from modular segments, each section independently absorbs vibration, temperature expansion, and seismic forces, a necessity for trains traveling over 300 kilometers per hour. The Magdeburg Bridge. A river flowing over another river. This looks impossible at first glance. The Magdeburg Bridge is the world's longest navigable aqueduct, carrying ships over land instead of letting them travel through it. Before this bridge existed, cargo ships had to unload, travel on roads, then reload again, wasting time, fuel, and money. Engineers solved this by building a water-filled bridge, allowing vessels to sail straight across. The hidden engineering challenge wasn't the bridge itself, it was the water. The structure had to support thousands of tons of moving water, while staying perfectly level, leak-proof, and stable in all weather conditions. To achieve this, engineers used reinforced concrete, expansion joints, and flexible seals that allow the bridge to expand and contract without cracking. Even temperature changes and ship movement were calculated in advance. Fourth Bridge. Completed in 1890, the Fourth Bridge was one of the first major structures made entirely of steel, and it's still standing strong more than a century later. Its secret lies in a revolutionary design called the cantilever system. Instead of relying on a single span, the bridge balances massive arms against each other, transferring forces safely down into the ground. At the time, engineers were terrified of bridge collapses, so they over-engineered everything, using far more steel than necessary by today's standards. That excess is exactly why the bridge survived storms, heavy trains, and over 130 years of constant use. The bridge was also designed to flex slightly under load, preventing stress buildup and metal fatigue. Akashi Kaikyö Bridge. The bridge is the second longest suspension bridge span in the world, stretching nearly 2 kilometers between its two main towers. But its true engineering test came in 1995, during one of Japan's most powerful earthquakes. The ground beneath the bridge shifted, and the distance between the towers changed by almost 1 full meter. Instead of collapsing, the bridge adapted. Hidden inside its design are massive flexible steel cables, seismic dampers, and expansion systems that allow the entire structure to move independently from the ground. The bridge isn't rigid, it's intentionally flexible. Millau Viaduct Bridge. The Millau Viaduct is the one of 2 tallest bridges in the world, with its highest pillar reaching 343 meters, taller than the Eiffel Tower. Spanning a deep valley in southern France, the biggest challenge wasn't distance, but wind. At this height, strong winds could easily destroy a rigid structure. Its ultra-slender deck is supported by cable-stayed pylons that distribute forces evenly, while aerodynamic shaping allows wind to pass through instead of pushing against it. Each pier is hollow and independent, meaning movements in one section don't transfer destructive forces to the rest of the bridge. Chenab Rail Bridge. The bridge is the highest railway bridge in the world, rising 359 meters above the river below. Built in a remote Himalayan region, engineers faced extreme winds, earthquakes, freezing temperatures, and almost inaccessible terrain. The bridge uses a massive steel arch design, which naturally distributes weight outward into the cliffs on both sides. This allows the bridge to carry heavy trains while remaining remarkably stable. Hidden inside the structure are wind dampers, seismic buffers, and expansion joints that allow the bridge to withstand winds up to 266 kilometers per hour in strong earthquakes. Even sabotage and blast resistance were considered. The Øresund Bridge. The bridge connects Denmark and Sweden, carrying cars and trains across the sea. But halfway through, something unexpected happens. The bridge disappears. Instead of continuing across open water, it dives underground into a tunnel through an artificial island called Pebberholm. And this wasn't for aesthetics, it was pure engineering necessity. A tall bridge would interfere with air traffic from Copenhagen Airport and disrupt ship navigation. So engineers combined three structures into one seamless system: bridge, island, and tunnel. The hidden challenge was managing wind, waves, traffic loads, and water pressure, all at once.